So I'm gonna quickly talk about, as already mentioned, the iCE40 USB trace. I'll start with a quick description of the project, where it came from, what it does, and that's that kind of stuff. Then we'll dig into the exact stack that's implemented, all the way from the protocol description, then through the hardware, gateway, firmware, and the software stack we have, and the kind of user mode utilities. There will be a small demonstration that I forgot in the outline, and then a few final words. So let's get started. So what is the iCE40 USB trace? Well, as you probably saw in the talk description, it's a low-cost, full-speed USB protocol tracer that, as the name indicates, is based around the iCE40 FPGA. It's obviously a dedicated hardware board that you can see in the picture here, but my hope is that it's also more than that, and it's a framework that can be easily reused on different boards, because really on this board there is not that much more than the FPGA, which means that a lot of iCE40 dev boards could be used to run that same gateway, firmware, and stack, so that if you happen to have like any iCE40 dev board around, you can possibly turn it into a full-speed hardware protocol tracer when you need one. So why would we want to do such a device? Well, the idea and main motivation came from Sysmocom, that contracted me, and the project was done in collaboration with them, because basically there was a customer need. They were using OpenVisla boards integrated into a larger assembly in one of the products. Unfortunately, due to the chip shortage, building OpenVisla became sort of impossible, at least at decent price, because mostly the Spartan 6, at least, was very difficult to find, and possibly still is difficult to find. So the fallback was to basically make a complete replacement that would be a drop-in, so that most of the things in the larger product didn't need to be changed. One thing that was helping is that only full-speed USB tracing was required. The OpenVisla obviously can trace, low speed, full speed, and high speed devices, but for this particular application, full speed, which is like the 12 megabits version of USB, was sufficient. So that was kind of the main commercial motivation. And another, motivation was to try to make hardware full speed analysis more accessible, and because lots of microcontrollers used by hobbyists are full speed only. They don't need high speed tracing. So it's still something that's very useful in its own. And if we can make it run on widely available hardware or dev board that people might have around, that means that if at some point they need to debug something, they can look in their stack of dev board, find an iCE40 dev board that's compatible, and run that stack in, and then bam, they have like a hardware USB tracer, basically. So if we look at what were our alternative if we didn't want to develop a new device, or if a hobbyist wants to trace USB full speed, the first one is just using a logic analyzer and something like SIGROC to do protocol decoding. Now, unfortunately, to really decode reliably USB full speed, you need a sampling rate of at least 48 megasamples per second, which means that the cheap, FX2 based logic analyzer that costs like $10. There are firmwares where you can run them at those speeds. Unfortunately, it's really not stable. Like I can only get it running for like a few seconds, and then it crashes because some buffer overflow or something in the USB, because it's really not something they're designed to do. And they can kind of top at 24 megasamples per second, which unfortunately makes the captures not decodable really by SIGROC. Of course, you can use fancier logic analyzer. I've done USB captures with my Agilent scope and stuff like that, but then you're limited by the memory depth of your scope. You can try to work around that with segmented capture and stuff like that, but it's really not all that practical. There's the OpenVisla, of course, which is a design that has existed for many years now. Unfortunately, as mentioned, it's not really manufacturable right now, and so it's hard to find. It's not super expensive, but it's also not dirt cheap, right? There is Luna, which is like the new USB multi-tool kind of board done by Great Scott Gadget. Unfortunately, it's also been hit pretty hard with component shortage, which means that the pre-orders that they took for the crowd supply campaign in 2021 are currently expected to ship in June 2023. So again, at the time where this project was made, no way to buy them. Also, I didn't satisfy even all the requirements, but anyway. There are obviously commercial options. Those are rather expensive. Some are very well known, like the Beagle USB, things like that. Not really an option for most hobbyists. They don't want to spend like $500 or $1,000 into a USB analyzer. There are some other options. I mentioned here too the 5 watts per USB, the GridFET one. Those were not really designed for USB analysis, which means the capability kind of varies, and yeah, they were not really made for that. You can use them in a pinch if you happen to have them, but yeah, not ideal. So what were the requirements when we started this project? Well, there are some strict requirements because they were driven by the commercial needs. The first one is it had to be mechanically compatible with the OpenVisla. It had to be like a drop-in replacement, which, you know, it fits exactly where the OpenVisla would go. Something else was to guarantee no interference with the device under test, even if the iCE40 is not powered, it's not configured, or the OS software isn't running. In absolutely all cases, we cannot interfere with the DOT. The DOT has to never know that it's being tapped, which is something that not all analyzer support. Sometimes you need to have them powered first before connecting to DOT, that kind of thing. Like, think, you know, if you connect the tapped USB bus directly to some FPGA I/O, you're going to end up backpowering the FPGA through its I/O, or when it's not configured, the FPGA happens to have pull-ups on those I/O. Suddenly you're pulling up the USB bus, which might trigger a detection, even though there is no device plugged in, that kind of stuff. That cannot happen. We only have to deal with full speed USB, as I mentioned before. And even kind of better is we know that the target DUTs are not using the entire bandwidth of the USB bus at all time. But there might be bursts on the bus, you know, short bursts of high bus utilization, but in average, we're not saturating the USB bus at all. Obviously, it has to be manufacturable, which means it had to use parts that were actually available at the time, and preferably at a decent price. There's some nice to have for this project, where, as I mentioned a few times before, is that I wanted a maximum of the parts of this to be both reusable and reused, which means like reuse a maximum of the know-how and the IP cores that I used before to kind of minimize the development time, and just reuse things that were already existing, among other things, you know, stuff that were in the iCE1 USB, for instance, that kind of design. And I also wanted the final design to be more or less easily portable to other boards, and kind of have a sort of a modular architecture on that. So the few design decisions that were made to try to satisfy those requirements were, well, yeah, we're gonna base it on the iCE40. The chip is somewhat available, you know, at some point it wasn't, but then it was. We considered other options, including some Go-in FPGA, things like that. The Go-in were more available. Unfortunately, the state of the open source toolchain at least was not as good. There were also slightly smaller devices, which mean that we might have needed an external microcontroller to do the actual USB interface, and then, you know, there's the availability of that microcontroller and how does it talk to the FPGA, that kind of thing. So in the end, we just settled on only the iCE40 That's also what makes it more portable, because if you're using a combination of microcontroller and FPGA, you have much less chance of finding, another dev board that has that exact combination connected the same way, for instance. The link up to the controller is going to be USB full speed. What I mean by controller here is the PC that's actually monitoring the bus, not the device, not the device under test. Sorry. It's pretty much all we can do with the iCE40 anyway. You could try to connect an external PHY, but again, that hurts portability, and it would be really, really stretching what you can do in the iCE40, so not a good thing. While for USB full speed, you pretty much just only 3 FPGA I/O and a few external passive. Now that means that if the DUT bus is fully utilized, we cannot uplink the entire day in real time to the controller. And that's why we added an external RAM buffer, which is basically gonna, whatever burst of full bus traffic, we can temporarily put it on RAM and buffer part of it, and then send it a few seconds later to the controller. We're using SPI PS RAM chips, which are available. There's no multiple manufacturer that sell them. You can find them on Mother, you can find them at LCSC. And they're very cheap. Like they cost like 1.5 euro or 2 euro, like maximum. I've used them extensively in several iCE40 design. I have all the IP cores to interface with them, so it was really a no-brainer. And if we assume that the protocol that we use to send the packets up to the controller is like 80% efficient, so that we only have like a 20% or so overhead compared to what's on the DUT side of the bus and what we need to uplink to the controller. With a 64 megabits buffer, which is like 8 megabytes, we basically have enough buffer to absorb 25 seconds of full bandwidth DUT traffic, which in my opinion is pretty good. I doubt that there is many cases that you would hit where you would overflow the buffer without somehow managing to extract the information you're trying to extract from there. We're also using some external CMOS buffer. This is to ensure the no interference, basically, and to kind of make sure there is an isolation between the DUT side and the FPGA side, because we have less control onto what the FPGA I/O are doing when they're unpowered, while on the other hand, you can find CMOS buffer that are fully specified for what's called the partial power down operation. Okay. Give me a second to. Okay, so now we're gonna deeper in the stack, starting with the protocol and then the hardware gateway, the actual boot process, how the firmware comes online, what the firmware does, and then the actual software stack we have running on the controller PC. So the protocol, we decided to go for like just a raw byte stream, basically, which means that we're not using any kind of USB defined framing when we send packet up to the controller. It's just a stream of byte. This is done both to minimize overhead, because if we were trying to use USB framing to basically encapsulate USB packets, well, the maximum size of a USB packet is 64 byte in full speed, which means that if we needed to send that to the host plus some metadata, we would at least need 2 packets and all the associated overhead that goes with that. And it's also good to maximize portability, because we don't actually depend on USB being the actual transport to the controller. We can imagine some other way of connecting the iCE40 to the controller PC. Now, of course, that byte stream is somehow kind of framed and so contains packets. We have a fixed 32-bit headers, which is basically all you're transmitting for most types of packets, except for data 0 and data 1 kind of type of USB packets. Um, and that header will contain the PID. The PID is basically describe what kind of USB packet it is. So a quick refresher on USB. Uh, I didn't mention that before, but in case you're not familiar with USB, USB sends packets on the wire. Those packets have different types and different types of information. A lot of them are very short and have kind of a management type packet. We call them either starter frame, handshake packets, or token packets. And then there is the packets that actually carry data, which are of type data 0, data 1. And that's what we need to send to the controller. And so for most types of packet, except for data 0 and data 1, we only need to send that 32-bit header, and that 32-bit header will contain all the information of the packet, the packet type, the good and bad flag, which basically mean was that packet correctly decoded and is valid. Some small data, only 11 bits, which depending on the type of packets will contain different information, like the address and endpoint for in, out, and setup packets, which are the token packets, the frame number if it's starter frame packets, and the length of the data if it's data packets. We also send a timestamp so that we know exactly when a packet was received on the wire. The precision of that timestamp is 24 megahertz tick, which is basically alpha symbol. And then following that header, if it's a data packet, we send the actual data that was exchanged on the bus. We include the CRC16 in that packet, which means that even a 0-byte data packet still contains the CRC16 that we need to transmit. So I'm gonna quickly talk about the efficiency of that protocol and what kind of overhead we're looking at. Now, some of the numbers, I won't go through all the computation. You can read the slides after if you want, but I feel that's going to be a little too technical and annoying. I just wanted them there to reference. But basically, every time we need to, there's two sources of overhead, sorry. The first one is that byte stream, we need to send it to the host, and we need to encapsulate that in USB, and we're paying a price for that, which is the classic USB overhead, basically. And then there is also the overhead that comes from taking the packets that are on the wire and somehow adding the metadata and converting them to our byte stream. So the first overhead, for every 64 bytes of packet that for every 64 bytes that we're sending to the controller, we basically need to send 77 bytes of data on the wire to the controller. That's the packet header on USB and stuff like that, which means that for every 1 byte we want to send, we're actually paying 1.21 bytes. So that's kind of the overhead at that location. Now, if we take that into account and we look at the efficiency for every type of packet that we listen to from the DUT, and what's the total efficiency? For the token packet, it's pretty good. We're actually 104% efficient, which means that we actually compress data. Now, that comes from the fact that we don't actually, those packets have some redundant information for error protection. We don't actually transmit the redundant information because we don't need to. We just check if it's valid or not and transmit the resulting good and bad flag. For handshake packets, we're unfortunately pretty bad because they're very short packets and we need to send more data about them than they actually contain. But the good thing is that USB will never transmit a handshake packet without a matching token packet just before, which means that those two efficiency kind of average out. For data packets, I analyzed two types, the empty ones and full ones. Now, if they're empty, again, we sort of pay cost in efficiency, and we're only about 69% efficient. If the data packets are full, we're about 81% efficient, which isn't too bad and somewhat in line with the 80% estimate that I did in the beginning. Now, those were for overhead at the packet level, but what's more interesting is to look at the transfer level. So USB to transfer information will okay, I'll say always, it's almost always have a sequence of 3 packets, which is a token packet that tells, okay, a transfer will happen to this endpoint, to this device, then an actual data packet, which contains the actual user data, and then a handshake packet that's basically a ACNAC that says, okay, it was correctly received and I was able to receive it, or there was an error or something like that. So the classic sequence is that. And so when looking at those classic sequence, which is transferring 64 byte, transferring ZLP is a zero length packet, which is basically transferring a data packet of 0 bytes, and a transfer that somehow was not accepted, that was nacked directly. If we look at the efficiency, we see that we're basically staying, in the 80% range, which means that we can kind of count on that efficiency, which means that we can pretty much be sure that we'll have 25 seconds at full speed that we can listen without overflowing the buffer. You can double check those numbers. I won't. If you have questions, you can also ask them, but I just wanted them there for reference. So now we can start looking at the schematic. No, I realized that that's probably too small to read anything. But I will just go over the sections globally. So that's this part here is the FPGA. As you can see, it's basically the FPGA and nothing else. There is a LED that's directly connected. All the rest is direct connection, nothing really special, and all on that side is just power supply decoupling, really nothing special. Here we have the power section. It's simple linear regulator with a decoupling at the input and the output. The only kind of special thing is that we take care of the power sequencing that's required by the FPGA, which means that the 1.2 volt rail enables the 3.3 volt regulator, so that the core rail comes up first. Be careful when selecting the 3 volt 3 LDO, because the enable signal is driven from the 1.2 volt rail, which means that it needs to be enabled with a voltage, 1.2 volt needs to enable it. We have the classic serial debug console with the 2.5 millimeter jack. That's classic to a bunch of Osmocom projects. That's the USB section. We'll look into that into more detail right after. There's just a bunch of miscellaneous MISC things. The programming connector, a bunch of LEDs, and a user button. This is a 12 MHz oscillator that provides the reference mostly for the USB. It will be internally PLL to 48 MHz. This is the flash and the PSRAM. They are connected using 4 I/O lines, so like a quad SPI setup, and they're connected in parallel with just a different chip select line. So classic way of using SPI basically. So all in all, it's a pretty minimal iCE40 setup. Not much thing special about it, except for this part. So we're gonna look into that in more detail. So that's what I just said. So this is a zoom on the USB section. On this side, you have the connection to the controller. Now, it might look like a lot of components, but in reality, the only thing that's strictly required is this 1.5K resistor, because this is just EMI for the shield, this is ESD protection, and this is an EMI filter, and this is series termination. You could remove all of that and it would still work. So this is just to do things kind of properly. So yeah, it's the connection to the controller is pretty much direct connection to the USB to the FPGA IOs. This is the connection to the device in the test. So one connection is the host, one connection is the actual device, the host under test and the device under test. We're tapping both data lines using resistors. Now the purpose of those resistors is to try to minimize our capacitive loading and basically the impedance mismatch that we're introducing by tapping the lines. Try to make them as small as possible while still actually getting the signal out of it. This is just ESD protection. And then we get to those like CMOS buffer that I mentioned before. Those are the 74 LVC2G34. And if you look into the datasheet, they are actually specified for partial power down operation. And I actually did validate that myself, that if they are powered down and not powered, you can have power and signal applied to the input. It will not leak to their power rail, so there will be no current going from there to the 3.3 volt rail, and there will be no current going from there to the output either. And same thing, if you have actually a voltage here from a FPGA pull up or that kind of thing, it will not go and leak to the input under any circumstances. So this basically guarantees our isolation from the DUT side. However, if you want to port that to other board, again, this is sort of overkill in the sense that you can perfectly just connect this to FPGA IOs directly and it will work. I mean, that's how the first prototype was doing it, and it was working just fine. So again, these are like to make things, 100% reliable and stuff like that. But if you want to run this code on a random dev board to quickly analyze something, it's doable without having those in circuit. So yeah, that's what I just said. Now we can go to the layout. As I said, this needed to be mechanically compatible with the existing Opus Vizsla, which means that the all pattern was fixed, the dimension of the board was fixed, and the type and position of connector was also fixed, which means that we're using full-size USB-B connector and full-size USB-A connectors, which means it's a very roomy board. There's not that much on it. It was also made 2 layers just to reduce cost, and because we could do it, we didn't really need 4 layers. Most of the routing is done on the top, and we have an almost continuous ground plane on the bottom side, at least under every critical part and traces. There is no cuts. There's only some cuts on the edges. Yeah, so as I just said. So now we can move on to the gateway, which is basically what do we run on that iCE40 FPGA. So this is pretty much a typical system on chip that I run on the UP5K. On the top, you have a soft core, the PyCore RV32, which is a RISC-V soft core, which is connected through a bridge to 2 types of memory with a low latency. You can view the bridge basically as the north bridge of a PC that connects to the memory. You have 1 kilobyte of EBR, which is embedded block RAM, and then 64 kilobyte of single port RAM. Now, something that I need to point out, and that might be confusing, is that in the FPGA you have SPRAM, which is single port RAM, which is RAM that's inside the FPGA and only as a single access port, compared to the EBR, which are dual ported memory. And then we have external PSRAM, which stands for pseudo static RAM, and that's an external chip. So yeah, don't confuse SPRAM and PSRAM. Now that I said that, the embedded block RAM is mostly used as a boot ROM. It contains the initial boot code, simply because the SPRAM is a large memory, but it cannot be pre-initialized, which means that we can't put some boot code in it because it can't be initialized. So we need like a small amount of EBR just to boot the SoC basically. Now the bridge also interfaces to a wishbone bus. It acts as a wishbone master and address decoder to select which peripheral is accessed. Now we have 3 first kind of utility peripherals here. The first one, DFU helper, it just helps reboot the SOC so that we can switch to the bootloader mode. We have the debug UART, and then we have a RGB LED controller, which is, make the LED show the status of the system, basically. Then we come to this, which is the Quad SPI system. We have the controller. The controller is interfaced through Wishbone, mostly for control, not so much for, you can transfer data through this, but it's rather slow. It's not very quick. But the QSPI controller also has like a DMA port, which is like a burst access port for like the high bandwidth stuff. The PHY that's used here is a dual rate PHY, which means it runs at basically twice the system clock frequency. Now this entire SOC, most of it runs at 24 megahertz, but the external SPI interface actually runs at 48 megahertz. No, given that we're using a quad SPI mode at 48 megahertz, that gives us 24 megabytes of external bandwidth, which is more than enough because like a 12 megabits USB bus that we're tapping is, a maximum of 1.5 megabytes that we need to read and write. That's 3 megabytes. That's still much less than the 24 megabytes of memory bandwidth that we have access to. So there is really no need for more because, if needed, we could go to a 4x5. We also have those IP core available, but it's slightly more complicated. There's no need for that here. And it's connected to the flash and the PSRAM in parallel, although mostly only the PSRAM is used. The flash is only used at the very beginning during the boot process, like we'll see later. So this is the actual USB tap logic. We'll explain it later. I'll first explain this side. This is a classic instantiation of the NO2 USB device core, which basically makes the FPGA appear as a device, as a USB device to the controller PC. You just have the main device core that runs at 48 megahertz. Obviously, we need some kind of clock crossing to go from the SOC main clock domain 24 megahertz to this at 48. Then we have 2 kilobytes of ticks and 2 kilobytes of RX buffer. That is way overkill for this application, but it just so happened that's what I had available. And those buffers, those transmit and receive buffers, are also available through the Wishbone bus to the PiCo V32. There's also 64 kilobytes of SPRAM that just happens to be attached here. Honestly, it's there simply because this whole part here was reused from another project has this, and it's not actually used in that project, but it's there. We could easily remove it if we will find another need for those SPRAM. And the USB buffer bridge here has also like a DMA access port that basically allows direct burst writes from the outside directly into the USB transmit buffer. Now it's done that way so that the PiCo V32 never actually has to see the byte stream that we're sending to the host PC. It just gives command to DMA them from memory directly into the TX buffer. So if you look at this part, which is really the only part that has been specifically written for this project, the entire rest of it already existed in one form or another in some other iCE40 projects that I have. But this had to be written. Now the beginning of it is what I call the USB tab block. We'll see what's inside that later on. But basically, it generates the protocol that I described earlier as a byte stream and pushes it to a DMA write block, which is descriptor based. So basically you give him, an address in memory and how many bytes it can write to that memory, and you queue several of those descriptors, and it will use them to write whatever byte stream it's received from this to the PSRAM. And once it's done writing a block, it just, signals to the PiCo V32, oh, okay, I've written 64 bytes or 128 bytes of byte stream to this address location. You can now use them. Memarbiter is just arbitration between the DMA read and DMA write so that they can access the QSPI memory controller. And then you have the DMA read block, which basically allows the Picore V32 to not have to, read the data from PSRAM manually and then write it to the TX buffers manually. It can just tell the DMA read block, okay, in that USB packet for this endpoint, just copy 64 byte from this address in PSRAM and tell me when you're done. When the DMA read signals to the Picore V32 that it's done doing that copy, the Picore V32 can tell the USB device block, okay, that packet is ready, you can send it whenever you asked for it, basically. So this is what I just explained, basically. Now we can look in more detail into that USB tab block, because part of it was actually also reduced from what was existing. So this is just the external circuitry and resistor and buffer. This goes through a file layer, which is really just the IO block from the FPGA, low-level RX, that's capture and clock domain recovery for USB, and packet RX is like a state machine that reconstruct packets and bytes, and also checks, CRC and that kind of thing to reconstruct packets. And all of that already exists in the NO2 USB core, so which I just split that part. I mean, I didn't have to split it. It was already split, basically. I just instantiated it in the USB tab module, and that gives me on this interface bytes of packets and some packet-related status that I can just tap to see what's happening on the bus. It has to go through some clock domain crossing because all of this runs at 48 megahertz. This gets passed to what's called the stream generator. And the stream generator is really what's going to look at the packets that are on the bus and generate the protocol that I described earlier. Now, one slight complication from this is that in the header, there is the data length of the packet. Unfortunately, we don't actually, at the beginning of a packet, we don't actually know the data length yet, because we will only know in USB, how long a packet is when we see the end of packet signal, which means that the stream generator actually has to internally buffer all the data of the longest possible packet, which in most cases is 64 byte for bulk transfer, but actually for isochronous transfer, that can actually be up to 1024 bytes plus CSE, so that's 1026. No, 25 actually, because it's 1023 the maximum size, not 1024. Which means that there's basically a 2 kilobyte buffer in this that buffers the packets. When it's been entirely received, it will prepend the 4-byte header to it and send it off to the outside. This is just a 8-bit interface with a strobe. There is no back pressure, which means that whatever is connected at the output here has to be able to receive the stream all the time at the maximum rate, or lose data, basically. So that's why after this, there is actually a small FIFO that absorbs the arbitration delay of the DMA write, because the DMA write might not be able to directly write to memory because it's currently reading from memory. So there's a small FIFO that absorbs that. Yeah, that's what I just explained, basically. Okay. So I'd like to take a second to explain the boot process of this, because it's the same boot process that's used in the iCE40 and in a bunch of projects that use the same DFU bootloader. But it's a little, not complicated, but let's say non-obvious. So the first thing that happens when you power on the device is that the FPGA will configure itself, from whatever is that flash address offset 0, basically. Now, what we put at that flash address is a very small, what I call the iCE40 stub bitstream, that only does very few things. The first thing it does is it will lock the flash. So the flash can be software locked, when you can tell it, okay, you cannot any longer write to the top 512 kilobytes of the flash until power down. Now that kind of protects the flash from accidentally erasing the bootloader and stuff like that, no matter what you load as the user bitstream or the user firmware. It also checks if the button is pressed. If the button is pressed, it will reconfigure the FPGA, what's called a warm reboot, with whatever is in flash at offset 256 kilobyte to 256K, and usually that would be like the real bootloader firmware, which is the NO2 bootloader bitstream and associated firmware. If the button isn't pressed, it continues down and instead reconfigure itself with the user bitstream, which in this case would be the iCE40 USB trace mains bitstream, which is located at offset 512K. And so that's in the part of the flash that can be actually user reconfigured or updated and that kind of stuff. Because even if you destroy that bitstream completely, well, the stub will still be there, and the bootloader bitstream at offset 256K will still be there, which that makes that process fairly resilient to user error or accidental overrides, basically. Now, once the iCE40 USB trace bitstream is loaded, I mean, it contains the sock that I described before, so it will start executing what I call the first stage bootloader, which is what is baked in the 1 kilobyte of embedded block RAM. You can find the source code in firmware/boot/boots, and this does very little thing. It's entirely coded in assembly. It's very small. It will issue a command to the PSRAM to switch it to QPI mode, because the memory controller cannot initialize that itself. It needs kind of external guidance or external commands to do that. Kind of like initializing the memory controller on the PC, that kind of stuff. It will then load 64 kilobytes of RISC-V code from the flash to the SPRAM, which is the internal 64 kilobytes of memory that the system on chip has. Now it will do that load in SPI mode. I'm not using QPI for the flash simply because if I switch the flash to QPI mode, if you try to reboot the iCE40 USB trace, if the flash happens to still be powered, it will remain in QSPI mode, and the hardware state machine in the iCE40 FPGA has no idea to reset the flash or to read it in QPI mode. It will assume that it is still in SPI mode. It will try to issue SPI command that will fail miserably, and the FPGA will fail to configure, and you will not be able to do anything until you unplug it, power it off everything, and replug it. So because we don't especially need any speed from loading those 64 kilobytes of code from flash to SPRAM, I just leave it in SPI mode. And obviously those 64K are the main firmware code, and so what's done next is to just jump to it. That main firmware code starts with what's in the start.s file, which is a very minimal C runtime in it. Initialize the data segment with whatever the initial content should be from another zone of memory. 0 clear the PSS, and then jump to the main and start executing the actual main firmware, which is what we're going to talk about now. So what does the firmware here does? I mean, I put it last, but one thing it does is all the USB housekeeping and kind of boring stuff, which is, handling the enumeration, returning string descriptors, device descriptor, that kind of thing, which is mostly handled with, code that already existed, that just basically the driver for the USB code, right? Nothing special there. Now, one thing it does is all the PSRAM FIFO handling. If you remember in the SOC description, you had the DMA reader and DMA writer, but in reality, there is nothing in hardware that forces that to be a FIFO. It's purely firmware that handles it as a FIFO, and or rather as a circular buffer. and commands the DMA reader and writer to, you know, read things until the end and then go back to the beginning. And the firmware is keeping track of what zones of memory contain valid data, what is the fill level. Um, it also reflects the fill level to the LED, so that by default, when capture is active, it's green, and it's progressively going to dark orange if the buffer fills, so that you have some kind of visual feedback that you might overflow soon. And then it does the actual USB protocol handling. It uses one bulk in endpoint to send data to the controller, and so it takes charge of controlling the USB core basically to send data from memory to the controller host, and it also and there's a very few control requests which are used to control the device. Very basic stuff. What is the status of the capture? Is it running? Has it overflown? Is everything okay? Basically, start the capture, stop the capture, and then get the current buffer level and also a buffer flush, which is clear the buffer, whatever is pending. Because when you stop the capture, you're basically stopping new packets to get into the FIFO, but whatever has already been captured is still in the buffer, and you still need to read it from that one in bulk endpoint until you get a ZLP basically. Then you're done. But if you don't want to bother reading because you don't care about the data, you can also just call buffer flush and be done with it. It will flush the buffer and reset everything. So that's kind of what the firmware does, which is really not that much, which is why the PyCoreV running at 24 megahertz is plenty enough and plenty fast enough to do that job. Okay, so now we can take a look at what we have on the software side of things, which is basically what's running on the controller PC. And that is a Python module, which is used similar to what the OpenVisla API has. It's not the exact same interface, so it does need some adaptation, but the concept are sort of similar, basically. It's based on Python libUSB 1 because we use asynchronous transfer submission to maximize performance, basically. You just instantiate a iCE40-usbtrace object. On it, you have like a few control like start and stop, which basically match directly to the control requests with some safeties added. And then you just call run, and it will run the main loop in the background. Now, if you have your own main loop and you want to do other things while this is running, you can actually call the handle event of the USB context directly. That also works, and then you can do other things in parallel in the same kind of thread. When you're creating that object, you're basically specifying a handler which will receive every packet that is received. It has to derive from that class, which has a single method, handle packet, and this method will be called with the actual packet that has been received from the bus. So that's like very, very easy to use to do your own stuff. One handler is provided kind of as a demo, which tries from the packet to reconstruct USB transfer. I mentioned before that a USB transfer was a token packet and a data packet and then a handshake packet in most cases, it's not all cases. And so here we have like a small handler that tries to reconstruct and match those three. It's very basic. There's a bunch of cases that it doesn't handle. It's mostly a demo, but if you need more than that, feel free to, send pull request basically. So the packets that are passed to your handler are derived from a class called USB packets, but it's not actually one class. USB packet is just the base class, but it's actually an entire hierarchy of classes, which can be data packets, data 0, data 1. They can be handshake packets, ACK, NACK, stall. It can be token packets, or they can be starter frame packets. And the data content from each of them is accessible through method. You need to look to the source to see what's available. They also all have in common like a header member, which basically gives you the metadata that are associated with that packet. Was it received correctly at all? Because if you get a bad packet, the CRC didn't check out or something like that, we're still gonna report it. But you have to know that that packet, what's in it, maybe it's valid, maybe it's not. The you get timing information as to when that packet was received, both absolute timestamp ever since the capture was started, or timestamp relative to the latest start of frame packet, which gives you like the position of the packet within the USB frame, basically. You can also call raw bytes, and raw bytes will return you like what would have been the raw bytes of this packet on the wire. Now I say would have been because, I mean, if you followed at least, you know that we do some packet parsing, and so some of the fields are not sent exactly in the same order, for instance, on our protocol than they are on the DUT side, and so there is some shuffling needed, and also some information we don't transmit at all. Notably, the CRC5 in some packets is not transmitted. So those we need to actually kind of reconstruct, basically. But it should still be a fairly accurate representation of what was actually in the wire, except for the CRC. We just know if the CRC was valid or not. There's a couple of demo utilities that are provided that are perfectly usable, like for basic analysis. It's pretty much all you need, and that's pretty much all what the OpenVisla sort of shipped with anyway. If you don't want to make your own application, the first one is print packets, which, as the name indicates, prints the packets. Big surprise there. That's just the demo run. You can see, it prints the starter frame and the frame number, and then if it's a ACK, you just see ACK. If it's a token packet, you can see, it's a setup to address 0 to endpoint 0, and then the data that's exchanged, stuff like that. So it's very raw information. Here you have the absolute timestamp, and here you have the relative timestamp. You have the frame number here, and then how much time after the start of the last frame it was received. So for instance, here you can see that the start of frame packets for frame 1728 was received exactly 24,000 ticks, and each ticks run at 24 megahertz. It's basically been received exactly 1 milliseconds after frame 1727. So yeah, USB frames are 1 millisecond. No big surprise there. But for instance, here you can see that it jumps from frame 1730 to frame 1786. Now, in reality, there's been a USB reset that has happened in the middle here, because I don't know. That's how Linux enumerates things. It does a first query, then reset, and then does a second query, whatever. Print transfer uses that kind of default handler that I mentioned before that tries to reconstruct transfer. So you've got something that's slightly more readable, where it tells you, okay, this is a setup transfer, and this was the payload, this was an in transfer, this was the payload, this was out transfer, stuff like that. No, the decoding isn't perfect, and you can actually see an example here. Like, this makes no sense. You've got a setup transfer, and then you've got in, and then something. And what it's actually printing here is actually because these three transfer were nacked, and somehow there was a bug in the handler that made it that it wasn't handled. So take this with a grain of caution. This is definitely correct. This can definitely have some bugs in some cases. Now, another software that's usable with the iCE40-usbtrace is VUSB. VUSB is a USB analyzer software that was originally started. I think it was started by Kate Temkin when she was working for Great Scott Gadget, and the main target was Luna, but it has currently backends for the Great Fed, OpenVisla, and the USB-Mon sort of software, USB tap on Linux. And I did make a driver for it for the iCE40 USB trace. Unfortunately, I did open the PR in last September, but really there hasn't been any project activity since January 2022. They kind of abandoned that project. It definitely had some issues, and they kind of moved to another project called Packetry that I'll talk about later. And so now they're focusing their effort on that second project, which is kind of the successor. So this is kind of abandoned, but still there's a driver for it and it works and it can help in some situation. It's a case of using the right tool for the right job, basically. Okay, so time for a short demonstration, which let's hope will work. So let me share my screen. See if that works. Okay, so hopefully you can see the screen. Yes, you can. So I do have a USB trace connected here. That's just a USB serial converter, nothing special, just to serve as a DOT. This is connected to this machine here, which is called Up Squared, which is like a small embedded thingy, which is serving as my USB host. This is connected to my main workstation that's going to run the software. So the first thing I'm going to do is to show the firmware update process. So it's using DFU. So I do have a pre-built bitstream and firmware. If we look at the available devices, you can see there is two of them. This is the one we're interested in. This is another DFU thing attached to my PC. So I'm gonna update the bitstream first. For that, I'm just gonna select the device and I'm gonna select it by serial number here, just this. And I want to flash. So you need to specify an alternate number. Alternate 0 flashes the FPGA bitstream. Alternate setting 1 flashes the RISC-V firmware. So I'm gonna flash bitstream first. So it's gonna reboot automatically. It goes to bootloader mode, which means you can see the LED start blinking blue, and then does the flash. And it will stay in bootloader mode because I didn't tell him to reboot, but I can no flash the RISC-V firmware. And here I can reset after, which will make it fall back to user mode, basically. So if I do that, it flashes, and now it's back in user mode. You see the LED is off. And if we look at the message, we can see that, yeah, here it disconnected. That's when it rebooted into DFU mode. iCE40-usbtrace DFU mode. And this is it rebooting with the new firmware. You can see it's the iCE40-usbtrace. So I'm gonna show here the message from the target, basically. Here. And I'm gonna try basically those two utilities one after the other. So for that, I'm gonna enable my Python virtual env in which I installed all the required packages. So the USB trace. So if you go to software, you have the print packet. So the LED became green, telling you that the capture is in progress. Now, obviously, it's not doing anything because there's nothing plugged in. But if I start plugging in the device, yeah, it was very, very fast because, yeah, USB transmits a lot of information. but we can see, hopefully, yeah. Here there was some traffic, including like the enumeration and things like that. I don't know if I can, yeah, I can actually scroll back to the beginning. So we can see here the first start of frame that's received, and the first queries and stuff like that, and all the data exchange setup address and all that stuff. And obviously we can see it enumerating here. So, but as you said, with especially printing all the SOF, we could put an option to hide the SOF so that it's less cluttered, basically. But so let me try the second utility, print transfers. Again, it doesn't print much because there's nothing, but if I plug in the device, we can see that it only printed the transfer and the enumeration, stuff like that. And if on the DUT, for instance, I do a verbose LSUSB, that will actually query the string descriptor from the device, and you will actually see the query for the string descriptor actually appear here. Again, I'm going to disconnect this. And then finally, we can also try view USB. View USB. So I need to remember how that works. Okay, so I want to iCE40-usbtrace, and I want the TUI. So that starts the interface. If I plug in the device, again, we can see, like for instance, here the request for the string, prolific technology, the device descriptor, and we can dig in. And if let me actually retrigger LSUSB to -v, and I can see the string that have been requeried. Let me put that full screen. Yeah, this is more readable. So yeah, here you have the thing with some analysis where you can see things a little more clearly than in other things. But as I said, this software also has limitation. It becomes sort of slow when there is a lot of traffic. So yeah, use with caution. But it's nice to have as an available tool, basically. Now, one thing I will point out is that when you press quit, it doesn't quit. I have no idea why you need to Control-C, but I don't know. It happens with other backends, so I think it's a bug in the software or in my setup or something. Okay, that's what I wanted to show here. Let's go back to the slides. So that was for the demonstration portion. Now, a few final words. What can be done in the future? What a most obvious thing would be adding low speed support. I don't think that would be very hard because full speed and low speed are really similar. It's really just sampling slower, and this is very well isolated in one particular module, which is currently sampling, at 12 megasamples per second, and you just need to change it to sample to 1.5 megasamples per second. You also need to take care of the fact that J and K symbols on the wire are inverted, but it's really minor stuff. Something that would be possible to add as well is kind of hardware triggers and filters so that you don't send to the controller everything, but you have the ability to only listen to one endpoint or listen onto a certain type of packets, or to not send the data and just send the headers, that kind of stuff, in case you need, that capability. It would be nice to be able to operate without PSRAM and using only an internal, the 64 kilobyte of SPRAM, which are currently unused, to be able to use those for buffer. It's obviously much, much shorter, but for things, like initial enumeration or stuff like that, it would probably still be fine and still have a good usefulness, I think. It would need to be tested, but it would actually be fairly easy to test because you could limit the PS/RAM FIFO to only 64 kilobytes and see if and when you overflow in some typical use case. So that's easy to prototype and then implement it if that works good. The goal here would be to help with portability because random iCE40 dev boards, a lot of them happen to have PS/RAM. It's a fairly common peripheral to find on a lot of open source hardware iCE40 dev boards, but not all of them do. Of course, other transports currently using a USB connection to the controller, but other boards could have other type of upstream connection, basically, like the using a UART through an FTDI. It's slower, but if you have a buffer, that could still work fine. SPI and Wi-Fi. So a lot of, not a lot, but at least two boards I can think of have an ESP32 attached, and that's connected through SPI to an iCE40. And so you could imagine basically doing remote network attached USB full speed analyzer in case you don't want to be next to your device, or you want to be able to do that remotely, that kind of stuff. I think that would be kind of cool and kind of useful. So potential dev boards for that kind of work would be the BitC is probably the closer because it has a USB upstream connection and it has a SPI PS/RAM. So literally just changing the pin constraint file, you could just upload that design to the BitC and just connect two random I/O lines to the USB port that you want to tap, and that would work. The icebreaker, you can add SPI PS/RAM to it, either through like a small hack of stacking it on top of the flash chip, or through one of the PMOD. And it has both SPI and a UART connection to the host, so that would be something that would be also doable. The iCE5 wireless and the MCH22 badges have, as I mentioned, ESP32 attached, so they would work fine as well. I kind of skipped the next to the BitC. There was the iCE dongle, which is another board very similar to the BitC schematic wise, in the sense that it has also an upstream USB connection and a SPI PS/RAM attached, so it would also be very easy to port. And it has like a external flat-flex connection to which you could connect through a breakout, whatever device you want to tap. So these are all potential. There's a bunch of other iCE40 dev board. These are just the ones that I happen to have personally, and that would be suitable candidates. Now, on the non-hardware side of things and non-gateway side of things, Packetry, which is like the successor to USB, which is much faster, actively maintained and developed. Unfortunately, at least unfortunately for me, it's written in Rust, and I have absolutely no clue how to write Rust code. But if somebody who is familiar with Rust wants to write a backend for the iCE40-usbtrace, that would be great. Yeah. I see that a couple of people are typing. Our reward is Wireshark. Well, feel free to use to write a Wireshark like a source for it. That's also welcome. So something yeah, true. Wireshark has an open Vizsla thing. Yeah. I'd like to say a big thank you for Sysmocom, since they both sponsored my work on this and also dedicated some resources on their side for the actual hardware design and producing boards and the software library and testing and that kind of things. So that was a great project to work on. So thank you very much to them. And here is a few links that you can follow. There is not much, but it's just basically a link to the project on Git here, where you can find both the how to design and all the gateware, firmware, and software stack all in the same repo, and a link to the NO2 USB core, which is used as the basis for the USB tap core in this project. Obviously, there's a bunch of other IP cores that I wrote that are used in that project. You can find them as sub-modules of the project repo. And that's it. This was quite long. Thank you, everyone, for joining and following. Like an hour and 10 minutes. If you have any question, feel free to write them either in the chat or just through the microphone. So the impedance matching is not that relevant in this application, indeed, at least for full speed. But as you mentioned, we try to keep the tracks of the correct impedance and properly routed, so that if you happen to connect a USB high-speed device, it will work. I mean, the device will work, but obviously the iCE40 USB trace won't see any packets because as far as the CMOS buffer are concerned, the differential level of the high speed is just too slow to so Max is asking if basically a buffer overflow happens, if there is some event that indicates overflow, or do you have to request the status explicitly? No, I don't think there is an event at the moment. We could add an interrupt endpoint to signal that, but at the moment, the way you would so when an overflow happens, the capture engine stops and will not automatically resume. So you would notice an overflow because at some point you will be downloading the data through the bulk endpoint, and at some point you will receive a ZLP that tells you end of capture. And if you get a ZLP and you didn't call stop yourself, that means that an overflow happened, basically. No, it is signaled through the LED. Like the LED starts to be red and blinking to signal that stuff has happened. And if you do the call to get status, you will actually see that, yeah, the capture is stopped and it has been stopped because of an overflow. But currently it's not reported through an interrupt. Through an interrupt endpoint, I mean.
Yeah, would it be possible to force a high-speed device to low speed? Probably just use a full-speed USB hub in between, because it's completely passive, right?
Yeah, I mean, at least with this hardware, you would have to do that externally, possibly with using a USB hub. If you connected directly the FPGA IOs, you might be able to basically jam the high-speed detect burst, right? In this setup, it's not possible because in the hardware board that I'm using here, it's not possible because we've taken special care that the FPGA cannot possibly interfere with the tap device. But if you bypass that and connect it directly to the FPGA IO, it might be possible to jam the high-speed detect burst. But other than that, yeah, using an external hub, I guess.
Okay, thanks.
Thanks again, everyone.